See, traditionally, right, NLP folks have tend to look at you know as just bag of words, right? So that means they are just independent words. So they are not looking at what happens if they are related words, and can you start looking at one and two words being related, or what if four or five words, three, four, five, and six and seven, n words are all related words, and how do you model your system and start learning? It's a very complicated thing where traditional machine learning algorithms will not work, which is where again we are trying to use a deep learning network, and what we are trying to build is a natural language interface to SQL queries. See, one of our sister concerns builds a data cube product. So they build data cubes over Hadoop, and so the users tend to write very complex SQL queries to access and figure out things from the data cube. So what we are trying to do is to simplify that part completely, and have a natural language interface to it, but use our distributed deep learning network to actually generate SQL queries. It could be complex SQL queries, but we are trying to generate them from these, from the high-level English language specification of the same. So NLP is a very emerging application of these deep learning networks. Again, they are very useful in document relevance search. So where especially if you have large collection of documents and you have to find out of those what are the documents of relevance for you, and quickly, for example, typically people build reverse indexes and stuff like that for this. But it turns out, and of course the commonly used algorithm, the TF-IDF algorithm, the distributed the deep learning networks have outperformed some of those significantly. And of course, a lot of the driverless cars and navigation is happening by these the underlying system is you know in most of those cases is a deep learning network. Uh, so we'll quickly see a few more applications. So we have looked at some of these. So one thing which I would like to stress on is they are very useful in especially what's known as multimodal learning. So when, for example, you have maybe data from the say the customer calls or whatever, and there are tweets which the customer has written, and so you have audio data and text data. How do you combine that? So your traditional machine learning algorithms won't be able to combine both, but the deep learning networks can. So they're actually very good in such multimodal contexts. So you might be able to get lot more useful predictions if you are able to combine such multimodal kind of data sets typically. So we've looked at a few other applications. Then, of course, what we have been focusing on. I've just kind of given a view of what exactly are these deep learning networks and what is the math behind it to some extent. And then we've looked at few applications of it where it's pretty useful and things like that. But we are actually coming to the other part of the talk where I'm trying to talk about, uh, you know, see, as the number of hidden layers increases, right, what happens? The computational complexity actually increases because it takes huge computation to actually even do a single pass, when there are multiple layers, right? See, the prediction is nothing but a whole pass, right? So every layer, every neuron in every layer you have to compute, right? You have to do a sum product sum of all the inputs, the weights, and compare with the threshold, and give the output of that. Similarly, you have to do it for all neurons in that layer, and that might be thousands of neurons in every layer. So the computational complexity is like huge. For example, Google, who have demonstrated the cat learning deep learning network, right, which learned to identify images of cats, they had like 16,000 cores, in their network, and it still took them 3 days to actually train that network. I mean, that's a lot of time for training, right? So that's what I'm saying. The computational complexity is overwhelming. So that's what has motivated us to actually look at a distributed implementation of these deep learning networks, um, right? So this is where I come from, and I'm coming from a distributed systems background. So we are looking at, because last few years we've been looking at implementing a lot of machine learning algorithms to work at scale and things like that. So taking that to the logical next step, and trying to see if we can, for example, implement a distributed deep learning network, which can drastically reduce the training time. For example, we want it to be only a matter of minutes or hours at most, not go into days and for training. Um, so that's what we are trying to do. So Jeffrey Dean's work, it turns out that it's not exactly a distributed realization. So they had a central parameter server which will serve out the parameters, and every node in the system will, or every core in the system will actually go to that parameter server, pick up the parameters and keep learning and exchanging values through that central server. So what we are trying to build is a slightly different thing. So we want to avoid any centralization in this network. So what we have built is essentially purely distributed, based on a publish subscribe architecture, because we built it over Spark. I'm sure Spark is by now pretty familiar to people here. I think people have talked about Spark last couple of days. So we have been looking at Spark for quite a while. So logically, again, we would prefer to implement this over Spark. We also had an implementation of this over GraphLab, incidentally, before we came to Spark. We first, because it was a natural thing, right? This also is nothing but a graph of neurons, right? So we thought it's a graph processing kind of an application, so we'll build it on GraphLab, and we did that. And it turned out that, of course, GraphLab, using it is a little bit harder, and it's written in C++, versus the abstraction of Scala, and making it much easier to use, and things like that. So consequently, we kind of did it on Spark as well, and we've as a consequence, right, we've kind of figured out that Spark was much more easier to implement, and we've now done 3-4 different deep learning networks we've implemented. So starting from the deep belief networks to the what's known as the RNN, the recurrent neural networks. So we built both of them, and now in the process of building the convolutional networks as well. Um, so essentially, this is what we've been doing, some interesting work on top of Spark. It also turns out that Spark itself needs a lot more enhancements, and so we are in the process of figuring out some of those optimizations essentially, right? See, one of the things we are doing is the weight matrices. So each, so in this case, right, every node in the system has a view or has the whole deep learning network with it. So we are not cutting it, or not. So for example, GraphLab is very useful if I have to cut this and distribute it on different nodes and perform computations. So GraphLab, it will be very good at that. But what I'm trying to do is slightly different, because see, the complexity of doing that will be too high, and because I have to keep exchanging. See, every layer will have to give it its weights to the next layer, and so it has to be done like that, right? And so the learning is inherently very serial, sequential in nature. So a single network does not lend itself to parallelism very easily. So what we are doing is to only parallelizing the training data. So for example, if there are 100 training samples, right, and there are 10 nodes, each node will only look at 10 training samples, right? And but each node starts, so all nodes will start with the same deep learning network, and the initialization of weights will be the same. But however, since each node will be learning different training samples, they will all diverge. But there is, we have a way of exchanging the weights, right, from nodes to the other. That's where our publish subscribe system comes in and allows the weight matrices to actually be exchanged from one node to the other. And it turns out that we can actually do an asynchronous computation of it. So it's not necessary for example, a node can do certain batches, right, certain number of training samples, and then say that it can publish those results, and does not have to wait for the others to actually give their values, but keep computing. Because of certain results have been proven in this area, and we have kind of figured out that. So it's a purely asynchronous learning that's going to happen. So it's pretty fast. So none of the nodes, see, typically in these kind of computations, what would happen is if one of the nodes is very slow, right, that will impact, and so even others which are faster will have to wait for the slow node to finish and then only go. But in this case, it's a very smooth asynchronous kind of computation. None of the nodes have to wait; they just keep computing and exchanging intermediate results. And when somebody else publishes the results, so it would update its own weight matrix, whatever it has, based on the new input and whatever old it has learned. It combines these two and learns, right, and updates the weight matrices accordingly. So every node does this and purely asynchronous way, and bingo, we are done. So what happens is every node has only looked at, for example, we saw, right, only 10 training samples, but it is as if every node has looked at all the 100 training samples. The learning would have happened at the end of the training phase. So this is what we are trying to implement, and of course, building couple of applications to actually showcase the power of this. One of them is, we talked about it, right? One of them is the what's known as semantic compositionality, an NLP application to generate SQL queries from English language. The other application, again, I talked about was the image search, right? We're trying to do much faster duplicate identification in large image databases. The third application we are looking at is sentiment analysis of audio. So when you have an audio, for example, customer calls, call centers, customer make calls, can we figure out the sentiment of the customer, right? Then it might be very useful to do things, especially if this could be done in real time, right? Maybe quick actions might be taken and maybe certain offers may be made to the customer, or something else could be done to mitigate the strong negativity, if that is there. So being able to do sentiment analysis in real time, is a very useful thing. But it turned out that it's actually very complex because first of all, we have to have a deep belief network to actually extract features from the speech, right, from the speech, from the audio files. And then we needed a hidden Markov model to actually convert it into text. Then the text is fed into a recurrent neural network, which will actually, perform the the most important part, which is the basically understand the patterns in the speech, right, and figure out sentiments. So we are actually in the process of building these three different pieces now. So one is a deep belief network, which we have already built, building a HMM also, and then what's known as a recurrent neural network. So all these three are required to do sentiment analysis of audio. So it's turned out to be much more complex than what we envisioned initially. But yeah, we are doing it. So what we have been looking at is the motivation for going from ANNs to deep learning networks, and why, what's the need for a distributed implementation of these deep learning networks. And so like what I said, Facebook has one of them. So deep learning 4J is the other commonly used thing. Then a lot of the traditional AI researchers use what's known as Theano. So Theano is a math library essentially in Python, but that provides some of these deep learning networks also. So they use that, and so of course going forward, there are some interesting things we are trying to do. So each node, what we have built, right, each the deep learning network in every node, right, now that will be optimized very highly. So what we will do is to have this single deep learning network running implemented on top of GPUs. So so we'll have a distributed GPUs, which so every deep learning network will be learning very fast because it's running on a GPU. It will not run just on CPUs, but it's going to run on a GPU. It will be much faster, and there would still be distributions because training can still be distributed across multiple nodes and can still do it much faster. So this is what we are intending to do further. So we will very soon start looking at GPUs and optimizing the individual node implementations of the deep learning network that we have built so far. So would be happy to take questions if people have any. Yes. Sure. Mm-hmm. Yeah, we are actually trying to figure out what's the best way to do that. So, see, it turns out that it could be one way might be to integrate with CUDA, but the other way might be to, for example, make the Spark scheduler little more aware. So right now it's like a dumb scheduler. It just splits and sends it out. It does not even know the node capacity, nor does it know whether the node has a GPU or not. So scheduler has to be aware. So one has to make modifications to the scheduler, and even then, right, that may not be enough because you still need something which can, maybe a CUDA or something, which can take the computation and put it on a GPU and make use of those cores and GPUs and do it well. So that might still be required. Um, or maybe there are other ways, but yeah, we are in that process, trying to figure out what's required. But one thing we have figured out is Spark scheduler needs a lot of modifications. So we're looking at the code and Spark code, trying to figure out what are those modifications we have to do. So we're in that phase actually, and we will come to CUDA also. Surely we have to do that. Yeah. What is your other question? I'll come to you in a minute. Yeah. Yes.
Another question is about, you talked about autoencoder, particularly in the case of Aadhaar image searches.
Right. Right. Right.
So the autoencoder output is some feature vector or something that you compare, or what is?
See, basically the autoencoder output is nothing but just the identity function. So it just outputs the input itself. But somewhere in the middle, right, you will have the encoding of the image. So you just tap into the middle layer and get that encoding out and use that to encode every image, right? So you will, for example, if you have a 128-bit encoding, right,